but I think it started recording automatically,
Okay,
so we are okay.
but we have just 4 people attending.
Yeah, we'll wait for another 5 minutes or so, and then we can start.
Okay, please tell me because I am going to share and then I will not see your screen. Okay.
Okay.
And good morning, everyone. It's 10. It's supposed that we should begin, but we will wait 5 minutes for allowing more people to join. So it's 10:05. I think it's time to begin this webinar. Good morning, everyone, and welcome to this final event of the HYWARE project. You can see there also the title. This project was focused in developing some models and also to study some processes that could lead to the hydrogen obtaining from wastes, just to support the production of other renewable hydrogen, or just to substitute this electrolytic hydrogen in regions without this land availability. So this is the outline for today. This webinar will be composed of two talks. The first one is myself. It's about a general overview of the HYWARE project. And then Nicolas will explain more the modeling part of this project. Can you hear me now? Because, yeah, I'm working. Okay, just to put in context the project, you know that the European Union has an important bet for hydrogen. They think that this is a key tool to decarbonize our society, along with electrification and batteries and so on. And then one of the main drawbacks of hydrogen, of the renewable hydrogen linked to electrolysis, is that usually, or the most used renewables are intermittent. So you know that PV or wind has some intermittency problems, and this must be addressed to avoid blackouts or to avoid discontinuous supply of hydrogen.
Wait, Javier, you muted yourself. Or
Sorry. Yeah, do you hear me now? Okay.
oh, yes.
Yeah. Some other concepts about the coupling of electrolyzers with renewables, especially in the region of Madrid, is the huge land requirements for installing this PV that should feed the electrolysis plants. And so we need to look how to avoid or how to decrease this land requirements. So in this context, taking advantage of the waste generated in the region could be a good option, because we will have, again, renewable hydrogen, and we can just decrease, or we can also act, or the wastes can act as a backup alternative for electrolysis when to avoid these intermittency problems. So when we talk about wastes, we have direct waste that we can gasify these wastes, as Nicolas will explain later, or we can also take advantage of biogas. And you know, biogas is a mixture of methane and carbon dioxide, and then it can be used to produce hydrogen through dry reforming or through steam reforming. Then you can see just in one slide our approach, the rationale behind the HYWARE project. We look at for the development of the integration of hydrogen production technologies into the waste management system, municipal waste management systems, just to obtain this circular hydrogen. And we develop it, or we apply different tools to develop this the project. We have one experimental part just to develop enough information, experimental information, to be integrated in the models, in the simulation models, and after in a general decision-making framework to optimize the working of the waste management system. And then you have here, which is the main goal of our project, was to develop, as you see, a regional and, of course, sustainability-oriented model to optimize the integration of these different technologies into this local waste management system. So these were the outcomes that we have. We have this predictive HYWARE model that Nicolas will explain later. Also, our colleagues from the thermochemical process unit at INDEA made a deep experimental work about the biogas reforming, dry reforming in this case. And with all this information, we tried to integrate this hydrogen production in the hydrogen mixes, or in this case from the community of Madrid. And finally, all the results could be also a good support for policy making at the European or the Spanish level. So then we have these 5 specific objectives. You can see that we began more than 3 years ago with the modeling and simulation of some hydrogen production technologies as the classification of these wastes. And in parallel, our colleagues make this experimental work about the dry reforming of biogas roaring. And then with all this information, the previous model and the information coming from the experimental, from the lab, we also model that and we simulate that. All of these process models were integrated in our decision-making framework, the HYWARE systemic model. We then generalize and regionalize this HYWARE model. That means that we also integrated the HYWARE model with other specific waste management systems. For instance, can be from industrial waste systems. And in the last part of the project, this the HYWARE model was optimized, that was integrated also with energy models to determine the best mix of hydrogen production techniques. So to reach these objectives, the project was breakdown in these 5 work packages. The first one dedicated to the definition through modeling and simulation of the already available processes as gasification. We also estimated the CAPEX and the OPEX, and we also studied sustainability through life cycle sustainability tools. The work package 2 was developed to the lab work, and then all the information from these 2 work packages was mixed in work package 3, where we developed survey models to integrate it in the HYWARE framework. That was in the work package 4, that also includes the regionalization and contextualization of this project. And finally, we linked the HYWARE model to energy models to, as you can see, the compute the optimal regional hydrogen mixes. This is just general description of the project. The HYWARE project was developed at INDEA Energy with the 2 research units in collaboration, the thermochemical process unit led by my colleague, Dr. Patricia Pizarro, and by ourselves at the system analysis unit. It was planned to last for 36 months, but it was extended for 3 extra months. That means that we finished the project in last November. And with this, I think we can pass for the most interesting part of this meeting, that the scientific part. And this is just a short agenda of the talk of Nico that is coming in 2 minutes. You can see that he will address these 4 points. I will not read because I don't want to spoil the presentation of Nicolas. That was all from my side. I don't know if you have questions, but perhaps it's better if we go first to the presentation of Nicolas, and then we will dedicate 10-15 minutes at the end for any question that you have. So thank you so much again for attending. And I have not commented, but I think you have realized that this webinar is being recorded. If you have any concern about that, please, you should leave this webinar. Okay, thank you so much, and I will give the floor to Nicolas.
Hello. Thank you, Javier, for introducing the project. I will now lead with scientific results from the project itself. So please tell me if you can see the presentation in.
It's not in the presentation mode.
Now it
yes.
should. Now it should
Yeah.
be. Okay, so the title of the presentation is Calculating Potential Hydrogen Production from Waste Management Systems. And the outline will be something like this. First, a brief introduction. Then we'll go into the process level hydrogen production and the technologies that we have available to produce it in the context of waste management. We specifically focus on the modeling and simulation part for this section. Then we'll scale up from the process level of technologies to how to integrate them into advanced waste management systems and how we have to convert our current systems into systems that can actually produce hydrogen. And then these advanced waste management systems will be contextualized under a national and regional hydrogen mix to assess how these technologies can compete with other technologies that are foreseen to be very important in the hydrogen production from here to 2050. So as we all probably know, there is a great demand for hydrogen, and we expect it to increase and double in the coming years and more. So this increased production on demand will be covered mostly by electrolysis technologies coming from electricity. But there is a part of it that is expected to be covered with biomass and bioenergy. And the thing is that if we can actually use waste in this small part, we can increase our circularity and gain in circular economy benefits. This is particularly interesting in highly populated regions in which there is low land availability. This is, for example, the case of many cities across Europe and the world, but we are going to specifically focus on the case of Madrid, because as you can see on the image on the right, a great surface of it, land, is actually either urban areas, which are populated and thus generating waste somehow, and then we have a great share of protected areas. So there is not much space, as Javier said, to deploy renewable electricity production sources as wind or PV. But as I mentioned, there is a steady production and expected to grow as population grows, generation of waste. So now I will go into the hydrogen production technologies that we have available. Basically, there are two pathways. The first one is utilizing biogas generated in the anaerobic digestions that are commonly found in relatively modern waste management systems. These usually utilize the organic fraction of the waste and transform it into biogas that can be somehow reformed to produce hydrogen. There are several technologies in this project that were considered for the reforming section. We have dry reforming. Then we have partial oxidative dry reforming, which not only converts methane with CO2 to syngas, but also utilizes a part of the methane to be burned and cover the energy demand. Then we have steam reforming, which is very well known because it's a conventional way to produce hydrogen, although from natural gas. And then we have tree reforming, which is a combination of the three reactions. So on another section of the waste management systems, we will have what are rejects, basically part of the waste that cannot be utilized or recycled further. So it has to be managed somehow. It usually either ends up in landfill or goes to incineration units. So in this section of the waste management system, what we propose is to install a gasification unit that instead of producing electricity like an incineration would, it can produce syngas, which is a much more versatile product that can be turned into hydrogen with the proper treatment, which is usually a water gas shift unit to increase the hydrogen content, and then a pressure swing adsorption to purify this hydrogen. Since in this first section, we want to focus on the modeling and simulation of the technologies, I'm going to show you a specific case study that we carried in the project and we were able to publish. And it's specific to the dry reforming technology. In this case, we did a life cycle assessment of hydrogen produced through chemical looping dry reforming. And the interesting part is that we co-conceptualized this case study with laboratory researchers working in this particular technology in the thermochemical processes unit here at India Energy. And we not only assess the technology, which is already relatively novel in the case of biogas transformation, but we did it for a chemical looping configuration that utilized a novel catalyst, which was a perovskite-based catalyst. After that, this is our methodology. And what we proposed is an ex-ante assessment. So basically, we wanted to assess how this novel catalyst would perform once it was scaled up and it had a comparable scale to current developed technologies. So we conceptualized a scale-up. We implemented it in Aspen Plus. And with this simulation, we were able to produce an inventory that we use for life cycle assessment. And then we were able to benchmark and analyze these results relative to other conventional technologies. So in the bottom, you can see the concept for the simulation that we propose. First, we have the chemical looping dry reforming section, in which the syngas is generated, then the water gas shift and pressure swing absorption sections to purify this hydrogen. And with the PSA off gas, what we what we did was to send it to a power and steam generation section in which we were able to produce some electricity and a steam for the water gas shift section. So on the left, you can see the reactor concept that we were using. It's a chemical looping, so it has two operating modes, basically the reforming and the regeneration one, which were then translated into an Aspen Plus simulation, which you can see on the right. And there we have 4 main sections in which we have the biogas conditioning, also the air conditioning for the regeneration, and then we have the reforming and catalyst reaction. The operating mode is basically an Excel subroutine that allows us to specifically select the behavior that we want to reflect on the reactor, which comes directly from the results obtained by the laboratory experts in the thermochemical processes unit. So this Aspen Plus simulation, as I said, enabled us to obtain the life cycle inventory, which is shown on the left, which, when we perform the impact assessment, generates the results on the right. We see that we're assessing the CLDR, the bar in the middle for all categories. We have climate change, acidification, and resource use of fossil fuels. And then we see that the performance does not meet the regulation for climate change of RED 3, which is 3 kilograms of CO2 equivalent. But what we found is that the main hotspot is related to methane emissions from anaerobic digestion plants. This is because methane emissions for TIF, there are some leakages in these plants. And when methane is leaked, its climate change impact is quite high. So what we basically recommended for this process is to improve its performance relative to decrease the amount of biogas needed and also the heat demand. But also we had a great, sorry for that. We also recommended that anaerobic digestion plants should work on reducing leakage. So, sorry. Oops. Now I'm going to go into the advanced waste management systems. So this is the part in which we integrate our technologies into our real waste management system. So as I said, we are working on the case study, which is the region of Madrid. And in Madrid, which is a pretty big city with around 3.3 million inhabitants, the municipality sends its waste to the Maldemin Gomez waste management system, which is composed by a series of technologies, basically material recovery facilities, anaerobic digestion, composting, and waste-to-energy incineration. So that what we did was to translate it into a mathematical model that enabled us to connect the physicochemical characterization of the waste going into the system with the technical characterization of each process, the ones that I mentioned, that compile the whole waste management system to generate the system products and requirements, which are basically a life cycle inventory. This will allow us to assess different configurations and make comparisons from an environmental point of view of how changes into the system affect its environmental performance. But I want to highlight that if you look into even though it's a relatively complex scheme, if you try to find in the products in the right, you try to find hydrogen, you will not be able to, because as the system exists now, which is this configuration, there are no technologies that can specifically convert the available waste streams into hydrogen. So what we propose in this case was the following modifications to the system, which are basically are highlighted in green. And you can see on the top right, we want to divert the waste going into the incineration to a gasification unit that will generate the syngas, as I mentioned before, and then produce hydrogen. And in the bottom part, also in green, we want to add another biogas utilization pathway, which is the dry reforming of methane, in this case using more conventional catalyst, for the hydrogen production. Both of these units will be followed by the water gas shift, PSA, and compression for the hydrogen to be ready for deployment. But how to do this? This is already a relatively complex mathematical model written in MATLAB, and now we have to add more specific process models to the system. Our process models, as I mentioned also in the first section, are built on Aspen Plus. So connecting them to a already complex MATLAB model would be computationally demanding, and also a delicate workflow in which you have many files that are fragile, that are connected in a complex way and not very replicable. So we proposed another alternative, which was to use these models to build synthetic datasets by sensitivity analysis, doing a wide sensitivity analysis on the variables that we're interested in. So basically, what happens to the model when we change the feedstock composition or the operating conditions of the reactor. And this generates these valuable datasets that are abundant and are enough and reflect enough variability in the dataset to build a machine learning surrogate model that in this case we used artificial neural networks because of their good performance in addressing nonlinearities especially. And this basically enabled us to retain the thermodynamic insight from rigorous Aspen Plus simulations and embed them into our MATLAB waste management system superstructure in a flexible and computationally light way. So this is all summarized in this much more simple diagram in which we go from data acquisition to the generation of surrogate models using machine learning and to the integration of these surrogate models into the waste management systems, which then we can use to perform the life cycle and landfill rate assessment as we desired. The first section highlighted in purple can be found in more detail in the paper on the left, which is the frameworks for the application of machine learning in life cycle assessment and process modeling. And the second part, which is more applied to the specific case that we'll be dealing with today, can be found in another study that was an outcome of this project, and it can be found in it's called Unlocking Advanced Waste Management Models. And then I will show you some results specific to the production of hydrogen and how it compares to a conventional waste management system configuration, which is displayed on the left, basically using incineration to deal with rejects. And then there were two bars on the right represent two different configurations using hydrogen, that are aimed for the production of hydrogen. In this case, we don't want to go too deep into the details because of the time that we have available today. But what we see is that when we introduce hydrogen into the system, our gasification performance increases a lot and is able to actually avoid some impact, which in contrast to the incineration facility. So this minimizes a lot the impact of the waste management system as a whole. So what we can conclude is that hydrogen production from waste has a positive environmental impact from a waste management perspective. And when we assess how much hydrogen we can produce hypothetically and potentially, especially potentially in this case, we see that the waste management system of Madrid, the one that only deals with the waste of the municipality of Madrid, could help cover a fraction of the estimated demand for the region for 2030 and 2040. But the thing is that the fraction that it can cover decreases over time because the demand is expected to increase exponentially as new uses of hydrogen become established. And yeah, so we see that potentially Valdemín Gómez could cover around 2% of the hydrogen demand for the region of Madrid. But this is a study, that number is very specific to the waste management system of Madrid and doesn't really consider that Madrid has other sources of waste and doesn't even consider how this waste-derived hydrogen can contribute to the national demand of hydrogen. So for that, we had to prepare a different assessment. In this case, it was a different type of model. It was not mass flow analysis, but an optimization model that was focused on considering as many technologies as are available for hydrogen production. By this, I mean, for example, electrolysis, gasification of coal, other fossil technologies, but all sources of electrolysis and electrolyzers. And for these technologies, we needed to characterize them very specifically with techno-economic parameters such as CAPEX and OPEX, efficiencies, lifetimes, and capacity factors. We also needed to clearly establish the demand for each region that the model is going to try to solve. And basically, a big data characterization. Also, for example, how big are the carbon footprints for each technologies and how they are projected into the future, because this is a model that will go from 2030 to 2050. And for each year, it will try to minimize the total system cost and basically determine the cost optimal hydrogen production and capacity deployment by region. This slide is a bit information dense, but this is all the information that compiles the model. I think it's more visually clear once we go into the results, because then we can see basically for a specific region, like Madrid, the one that I mentioned, it was our case study. And now we were not focusing specifically on the municipality or the city of Madrid, but expanding to the whole region, in which we had already mentioned that land availability was low due to protected and urban areas. So the options are not so abundant. And we had also characterized the demand for this region of hydrogen from 2025 to 2050. So the results of the model that I was previously mentioning are displayed on the left. And we see that most of the hydrogen will be covered by electrolysis. In this case, would be PEM. We will also have an important share of biomass gasification. In this case, it will not be waste, but general biomass like from other sources. But an interesting result is that we see that actually one of the technologies that we were assessing, which is the gasification of rejects from waste management systems, is present to sort of cover for a small part of the demand. It is not as competitive as the others, but it does have a role to play under the restrictions and details of the model that we proposed. This is an interesting result because it ends up backing up our initial hypothesis that this waste-derived hydrogen could have a role in this type of regions. But another result is that when we go to the national scale, the hydrogen from waste that we just mentioned gets completely diluted into the national mix of Spain, and it doesn't really have such an important role to play in other regions that do not have these characteristics. What we have to say is that this is all a projected model that goes to 2050, and that a lot of the technical characterization data that have been used to run this model are very uncertain. So the projections that we're showing here are sensitive to changes in these cost projections. Another result of this model is that it also enables us to see which regions of Spain, in this case, will have relevant import demand for hydrogen, which are basically the two in the north and the Balearic Islands. And yeah, with this, I lead to my conclusions, which is that relating the first study, which was the dry reforming of methane for hydrogen production, we found that the results heavily depend on reducing methane emissions from anaerobic digestion plants. We also found in the second section that hydrogen production is more environmentally attractive than conventional alternatives, such as incineration or upgrading to biomethane. And also found in the last section that hydrogen production from waste can help cover demand for specific regions with low land availability, but its contribution at the national level, in the case of Spain, will be small. And lastly, I just want to thank, of course, the funding that supported this project, the HYWARE project, and also my own grant that has supported me for the last couple of years. And also thank you for your attention, of course.
So thank you so much, Nico. So I think it's time for questions. So I think you can unmute yourself or you can write in the chat if you have any question. So I don't see any question.